I'd like to get us started here today for our latest What Physicists Do. Today we have Dr. Chris Boshuizen.
Yeah.
Okay, very good. He's the co-founder and chief technology officer of Planet Labs Incorporated, working in a field that they have dubbed Agile Aerospace. I had to say that because I read that and I thought that was very good. Agile Aerospace. Where they have designed, built, and they operate a network of Earth imaging satellites. Dr. Boshuizen has a bachelor's degree in physics, as well as a PhD in physics from the University of Sydney. We were talking about his PhD and how it's in astrophysics as well. And he has spent several years prior as a space mission architect at NASA Ames Research Center. I hope we get to hear a little bit about that transition from one of our national labs to the process of starting a company and working as both a co-founder and chief technology officer. Let's give Dr. Boshuizen a warm welcome.
So it's been a little while since I've talked in a lecture theatre without a microphone, so if you can't hear me, just wave and shout or throw something at me and I'll talk a little louder. So I wanted to just talk a little bit about what I did in school and how I got here to the United States. I'm from Australia originally, and how I ended up working in space and starting Planet Labs. And if I had sort of one motivation for this talk, it's how many people here? About 100? To start about 100 competitors for my company. I think that would be a great outcome from this talk. And I think sort of the moral of everything I'm going to say is that space, a lot of people think it's hard, but in fact it's easy if you do it the right way and you pick the right thing to do. And so let's have a look at why that might be the case. So when I was this is my fourth year honors work in, I'm actually not plugged into that, so I don't think it'll work.
Oh, if you'd like it as a laser.
Okay, cool, I can use this. Yeah, cool. So I was looking at archival data from the Voyager spacecraft. So Voyager had gone on this, Voyagers 1 and 2 had gone on this grand journey of the solar system, visiting some of the large planets. I was looking at electric field and magnetic field data from the two spacecraft as they visited the big planets, and I was trying to understand if the electric and magnetic fields were similar to Earth and what happened when the solar wind from the sun hit those planets, and if the physics was similar. And when you look at just satellites orbiting Earth, you have statistics of one sample. You want a bigger sample set, so my job was to look at other planets that we might have data for. And even though the physics was cool, I spent most of the time thinking about this lone little spacecraft drifting through space and its journey, and the fact that it's still working now some 30 years later. And I thought that was remarkable. And I realized actually that I was more interested in the space engineering than the space physics. And I think my professor had already figured that out years earlier and said to me that I was one of his weirdest students and I probably wasn't going to end up in academia. And his goal was to shepherd me to a path that would get me through a PhD and out doing something that I wanted to do. So that was a really cool opportunity. And when I finished my undergraduate work, we were quite fortunate that in Australia we got funding for what was our first space mission in like 20 years. And so this was a proposed spacecraft called MONS that was going to carry a 12-inch telescope, 12-inch diameter telescope, into space to look for planets and oscillating stars, much like the Kepler mission that's running out of NASA Ames right now that's discovered like almost 1,000 planets to date. So this was going to be a precursor to Kepler. So my PhD work was helping to design this instrument, which was a very sensitive, louder? Okay, sorry, someone was waving at me. Was a very sensitive telescope to look for minute vibrations in stars that are not the sun, so things like Alpha Centauri and stars even further away. However, unfortunately, the government changed and the funding was taken away, so this space mission sort of disappeared. So I got my first real-world experience of a complete space mission from cradle to cancellation. So it's very common. It will happen to many of you if you work in the space industry, so get used to it. Delays happen, launches are delayed. I'll talk more about that in a minute. So I changed my title of my PhD thesis from a space mission to a proposed space mission, and they were quite happy to accept that. So one of the ironies was to develop this extremely sensitive instrument, I had to model all of the stray light contamination coming into the telescope. For every photon from the star we were looking at, we actually needed to have a rejection factor of 10 to the minus 15 for any other stray light photons. The other way to think about that is that for every 10 to the power 15 photons coming from our target star, only one photon was allowed to come from our sun, the Earth, the Moon, Jupiter, so any kind of reflections. So we were designing this optical system. I was modeling the stray light. Here is what the stray light looked like on the detector as it was coming into the instrument, bouncing off all of the structure. I was trying to work out if how many photons I actually prevented from getting to the CCD. Thank God this thing never flew, because I was never sure if I did my job right. And just before cancellation, we built some of the elements of the spacecraft. So we actually built some of the filters, and down here, it's the only picture I could find, but this was the mirror for the telescope. So we made a lot of progress, but in the end, this thing didn't fly. I so hated doing the optics and straight light analysis at the time. After 4.5 years of doing the same thing, it kind of drives you mad. And when I left, I vowed never to do that particular kind of work again. And then 10 years later, I started a space optics company, which I find somewhat ironic. So the point is, even if it hurts, the pain does go away, and you'll want to do it again one day. So this next slide I actually think is really important. So this is a group of students at a conference that I went to. In fact, this was one, I think, where I was lecturing, but the previous 4 years I'd gone as a delegate. So my advisor gave me one really important piece of advice, which is, in your year before graduation, go to a conference that's relevant to what you want to do. And actually, we're quite lucky here in California, because between San Francisco and San Diego, there's almost a conference in every technical discipline that you might be interested in, whether it be the AGU in San Francisco at the end of the year, the American Geophysical Union meeting, which is, I think, 15,000 scientists interested in astronomy and heliophysics, all the way through to space science, space technology conferences. One of my personal favorites is the Cubesat Developers Workshop down in San Luis Obispo in April. So why this is important is, in the faculty of this school and the people you may not exactly have access to everything that you need. You've learned a lot, but you might not know where you're going to work. You might not know where to get an internship. You might even not know what to do next. If you go to a conference like this, you'll meet people that will inspire you, that might be your sidekicks on a grand adventure that you want to take on. And they might even start a company with you, like two of my co-founders who I met in 2002 at this exact conference series. So my best advice I can give you is get out to a conference, meet some people, make friends, and see what happens next. So out of that experience, one of my friends got a job at NASA Ames, and he'd been working on this little spacecraft. This is really cute. This was a low-cost lunar lander. It was 3 orders of magnitude cheaper than any spacecraft NASA had ever built before, capable of landing on the moon. So roughly, instead of $3 billion, it was about $3 million. That might sound like a lot of money, but by NASA standards, this was extraordinarily cheap. So in the end, they hired me to help drive this thing. So I took over the test program for a number of years and helped develop the control systems for it. This could fly around inside. This kind of looks like it's inside of like a basketball stadium, and there's like a net here. And this vehicle could actually take off and hover and fly around and land itself. And so we were developing code to land this thing on the moon. During that time, I signed 2 agreements with companies in the Bay Area to actually commercialize this and build their own lunar landers for the Google Lunar X Prize. Who's heard of the Google Lunar X Prize before? Yeah, so that's a roughly $25 million, $30 million competition to land a lander on the moon. And so, yeah.
How could you get permission to work outside and share that information?
That was a huge process. That's a great question. So the question was, how do you get permission to share information outside? So when NASA was formed in 1958, the Congress realized, and JFK realized, that to go to the moon, an extraordinary effort was required, and the government couldn't do it alone. So companies were essential to the life cycle of space in the United States. And so fully half of NASA's law, called the Space Act, is for NASA to actually support industry in the United States, and for there to be a flow of technology into industry, and for industry to build things, and for that to flow back to the government. So So NASA is, I think, one of only 2 federal agencies that can sign its own direct agreements with companies that aren't purchasing contracts. And so we had a mechanism that's roughly 50 years old now to get stuff out into companies. And these companies are now evolving this and building something really cool that NASA's buying back. And so that life cycle of technology out of NASA, spin-offs basically. And NASA actually publishes a book every year of the spin-offs from that year. It's usually maybe about 1,000 inventions a year. Teflon and Velcro were not one of those, but actually the power drill, the cordless drill, Black & Decker cordless drill, was a NASA invention. And that was invented for assembling the space station. So there's been a long history of sort of technology incubation from NASA. NASA evolved this project itself into this spacecraft called LADEE. This LADEE stood for Lunar Atmospheric Dust Environment Explorer. This satellite was launched in 2012 and did a 5-month orbiting mission of the moon, measuring the dust that rises off the surface of the moon as the sun goes around. So it's this really crazy thing where the heating of the surface causes some sort of electrostatic discharge that causes a column of dust to bounce off the moon in a large sheaf that sort of goes like a curtain around the moon as the moon orbits around the sun. Well, as the moon rotates and the sun moves around. Yeah.
Is that a photograph or a painting?
That is a CAD model, probably superimposed over a photograph. But I have another interesting photo I can show later if you. It's actually a real photo of it. It's like 6 pixels. But anyway, so this column of dust is really interesting because if you want to live on the moon, they didn't know about this before. They only found it very recently. And if you live on the moon, it's like a storm once every 28 days that comes across and throws up a lot of dust into the air, and it falls on things, so it could fall on solar panels. It could also be extremely toxic. The lunar dust the regolith is believed to be very spiky from millions of years of micrometeorite and molecular impacts. And so this dust that goes up might be a real hazard for human settlement on the moon. This was not known until very recently. So LADEE has studied that, and the results are still being looked at from the science data. But it was a really interesting mission. However, this $3 million lunar lander ended up becoming a $240 million mainline NASA mission. So somehow between starting it and being cheap and then carrying it through to completion, there was essentially 100x growth in cost. And by NASA standards, again, this was still pretty low. This is one of the cheapest missions NASA's done recently. But my colleagues and I were still sort of surprised that it could become that expensive so quickly in only a space of about 3 or 4 years. So around that time, I had a boss who used to pull his phone out of his pocket and wave it at conferences and talks, and he would say, I think it was an old phone, like it was a government-issued Palm Pilot. So not even a very good one. But he would wave it around and he'd say, my phone is better than your satellite. And that phone actually had more, his BlackBerry or Palm Pilot had more processor capability than the satellite. Because this still used relatively old technologies. At NASA, people really care about, if you're spending $240 million, you want to make sure that it works, right? So you use stuff you used before. That stuff is probably old and probably expensive. So anyway, he pulled his phone out of his pocket, he waved it around and say, this is better than your satellite, but he put it back in his pocket after that. So after hearing him say that for 2 years, my friends and I said, let's try it out. So the Google Android phones had just come out, and NASA Ames in Mountain View was right next to Google. So we had some friends at Google, so we were like, hey, can we get some Google phones? So there was this funny moment where these 2 guys from Google in their hoodies on their colorful, 4-colored little bicycles cycled around the street to us. And at NASA they have security guards, so they have guys with tasers and pistols, like real pistols and batons and everything, the whole works. So there's all these security guards. These guys cycle up in their hoodies and pull this giant Ziploc bag out of their pocket and just sort of pass it to me. It looked very suspicious. But inside were about 20 phones that were like hot off the press, and this was one of them. So the guards left us alone. But we put one of these phones in a vacuum chamber. So this is in a vacuum chamber at NASA Ames. We pumped the vacuum down to 10 to the minus 6 torr, which is reasonably good approximation of space. The phone was still working. So this is the screens on, kept running. This shouldn't have surprised us, but it did. And I remember we were all running around in circles, really excited. So we're like, this thing actually could work in space. So It's not surprising actually if you think about it, because most extremely small electronics are made in extremely clean, near vacuum-like conditions, like the chips and stuff. And these phones are so small now that they don't have really big components in them, like electrolytic capacitors that can explode in low pressure. So they have ceramic capacitors instead. And so this is generally vacuum safe already, which is kind of nice. It's kind of like going home, in a sense, from where it was made. So the other thing you want to test is, can it survive launch? So we did a number of rocket tests, strapping the phone up in a rocket and trying to see if it could do anything useful. And here's a cool video of us trying that. On the bottom, we have a graph of the phone's accelerometer. We wanted to see if the phone could actually be a useful instrument. So we're using the built-in accelerometers in the phone to measure the rocket ride. Then we have the rocket cam on the left, and then we have an outside camera on the ground here on the right, and that'll switch to rocket cam in a minute too. So check this out.
5, 4, 3, 2, 1. Real shit right there. Arkin. It's still going. Still going. Down, Arkin. Jesus Christ, that went on fire. Yeah, it's just a close to rocket. Okay. I don't care, I got CTO. I got there.
There you go. So that was our first science experiment with a phone on a rocket. Not all of them worked. This is another one that we did the same day, actually a couple hours before that video. This was a new idea that some friends of ours had, which was to build a two-stage rocket. The other one was a one-stage sounding rocket. So here they got 4 of them and strapped them together. So there's 3 at the bottom and another rocket, you can't quite see it in the picture, but attached to the top is another stage. So it was a first stage with 3 motors and a second stage made out of 1 motor. These are kind of like 4 or 5 inch diameter surplus rocket motors you can buy from the Army. I think they're used for Tomahawk cruise missiles or something. So they're basically solid motor cores that you can buy surplus and build rockets out of. So something went wrong on this rocket on the way up, and they had nylon pins that were holding the first and second stage together. And the idea was they had a little, basically a little shotgun shell in there that was on a timer that was going to explode, that would push those pins apart and separate the stages. However, the rocket got really hot on the way up, so the nylon pins melted, and the whole thing just sort of fell apart on the way up. And turned around, came back down while the motors were still burning, and went about 6 feet into the ground. So in the nose cone was a NASA experiment that was about 3 feet long, and the impact crushed that down to about 4 inches. And that ingloriously slammed onto the phone, and one of the bolts hit the top of the screen, twisting the phone and breaking the screen. But apart from that, the phone was still running. And we got our data off. So out of all of the experiments, I think there was like 7 or 8 experiments, we were the only one that got data. So this is like a third victory for phones, right? So at that point, we were like, we could definitely put this in space. And so we went and convinced NASA to actually buy us a rocket ride to put a phone satellite, which we call PhoneSat, in space. So this is the original concept for what PhoneSat looked like, which was basically an Android phone in a box. And to be cheeky, we really thought that we should launch the whole phone, screen and all, because we wanted to make a point that a phone would work in space. And if we did special things with the phone, that would sort of degrade our story. So this is the whole phone, screen and all and everything in a box. And that's why we had to fit it diagonally, because we couldn't take the case off or anything or make it smaller. And really all we did was add an extra battery, not exactly that 9-volt battery, but we added some extra batteries and plugged a radio into the USB port, because the cellular radios don't really work from space. So we added a UHF radio. Using one of the standard CubeSat kit boxes, this is what it looked like when it was finished. And you can kind of see here, that's the camera, if you can see that from the phone. That's the edge of the body, and then the phone, and there's I guess that's the back side. So the screen is on the other side. It's pretty simple. It's just really only 4 parts if you count the box, and the total cost at NASA prices was $3,000. So $500 for a phone. Yeah.
On the bomb tag or the room before flight, is that for deploying the antenna or arming the?
Yes. So CubeSats usually to fly they have 2 switches, and so one is this rod. There's a little rod that goes in that pushes one switch internally, which keeps the CubeSat off during transport and handling. And then there's another switch. I think
So it's the power up.
yeah, and then in series with that is another switch here, which is actually in the foot, and it's a little toggle switch. And so when you're in the P-pod, who knows what a P-pod is? So lots of rockets often launch with really big satellites on them, but there's a little bit of extra space, so they invented this standard canister, which is, they call it a P-pod because it looks like a pod and you put 3 of these cubes in, sort of like peas in a pod, and it has a spring and a door like a jack-in-a-box. So this would just slide in with 2 others, close the door, and when it's in space, they just open the door and the spring just pushes them out into space. So that switch here, when they're all jammed in the box, that switches in and the satellite's off. And so once the door opens, it'll switch on automatically. So that's sort of how that works. You have 2 switches, this one on the ground, that one in space.
So they're both power switches?
Yeah, they're both power switches in series. Yeah. So they both need to be removed for anything to happen. And this is a photo of us testing the phone sat from a balloon about a month before flight. And then in April 2013, we launched one of the phone sats. And to get the data back, we decided not to use a ground station. We actually advertised on the web that we were launching without a ground station, and that if anyone was a ham radio operator, they could help us download our pictures. So this is one of the pictures from the camera on the phone of the Earth, with little chunks that were downloaded from about 1,000 hams around the world. And it's sort of like giant global puzzle hunt. And that was really cool. So this project ended up being a really great outreach activity for NASA. About 1,000 people around the world were involved, and it proved that phones can work in space. At that point, my friends and I were kind of like going, well, this just worked. Like, what next? And so we thought, if space is really that cheap and actually that easy, and maybe when people say space is hard, they were lying. Maybe we should put our money where our mouth is and do something serious with it. So we left to start a company, which we started in my friend's garage in Cupertino, right next to Apple, just because we thought that was going to make us successful. So it turns out we were right. It was purely the garage. But interestingly, when we're in the desert doing that rocket launch, this gentleman here was there as well with his son launching rockets. His name is Steve Jurvetson, and he runs one of the largest venture capital firms in Silicon Valley called Draper Fisher Jurvetson. Turns out he just was a rocket hobbyist, and we didn't know that. So we met him there. We were talking about our project. He became a friend of ours, and he came around with his business partner, Tim Draper, this gentleman, and actually invested a small amount of money in our company while we were still in the garage. The secret to that was that we were just doing stuff. We seemed serious about it. He'd seen us in the desert. We were out there. We were energetic. We were enthusiastic. And when he came around, we were actually building a satellite in the garage. We were actually building it. And so we looked real. We weren't just, we didn't have like a paper business plan that we were just shopping around. We were just building it. And we actually said to him, hey, we're doing this anyway with or without you. So, do you want to join? And so he said yes almost immediately. And so setting up in the garage actually really helped us get started because we looked real. And what we built in the end was this spacecraft, which we called Doves. Most big sort of NASA, or not so much the NASA ones, but the military satellites have really evil names like Talon and Raptor and Hawkeye and Kestrel. So one of our friends was lamenting, why don't we call ours Dove? Sort of like peaceful. So we did. And so what my company's trying to do is launch a flock of doves to do remote sensing, to map the Earth every day. And so this Dove satellite, which is just a 3-unit CubeSat, so it's 3 times bigger than the PhoneSat one, has just a really large camera in it with a big telescope, has enough solar panels to keep it powered, and some extra radios again for telemetry and for downlinking the data. So in the spirit of sort of Silicon Valley, where it's important to release a MVP, a minimum viable product, and sort of iterate, we built the satellite in a number of different generations. And the first one that we launched wasn't actually finished. It was about 30% feature complete, sort of to steal language from the software industry. So we hadn't built everything. In fact, the radio, we didn't even have the high-speed radio. But we wanted to prove that we could, do what we claimed we could do, which was take a picture from Earth of this, from space that was valuable. So we ended up buying 2 rockets, and I thought it would be really nice if we had them about a year apart. So we could build prototype 1, launch it, learn some lessons, launch prototype 2, get some lessons, and then sort of launch maybe 100 of them in the constellation. However, rockets slip, as I mentioned, and delays can happen. So in the end, the rocket on the left, which was a brand new rocket, had never been flown before, ended up slipping about 2 years. This is a US rocket called the Antares. The one on the right is a Soyuz out of Russia, launches from Kazakhstan. It slipped about a year. So in the end, they were 3 days apart, which wasn't very good for iterating. But even worse, in this rocket, we were attached to the top of the rocket, to the second stage. In this one, we were attached to the capsule. It's kind of like the 4th stage. And that capsule was going to go into orbit for 3 days. So anyway, minus 3 days plus 3 days equals 0. So Dove 1 and Dove 2 launched 3 days apart, and our satellite, Dove 2, was released into orbit first, and we were watching the live stream of the Antares being launched. Its first flight, we were extremely nervous. We'd actually put out better spacecraft on that one, version 2, so we were more interested in version 2, which was probably about to blow up on this brand new rocket. So we were watching this, and just as that rocket took off from the launch pad, I had to yell at everyone, guys, get back to your computers. This satellite's about to go into orbit. And 20 seconds later, it went overhead, and we contacted it using the Stanford ground station, the big dishes on the hill there. And then 45 minutes later, this one went overhead, and we got contact with that. So it's funny how, thank you, 3 years of planning can compress down to literally 45 minutes of time. And my friend liked to say that's what he considered a stable configuration under Murphy's Law. Once something is going as wrong as it can go, it will continue to do so. So anyway, but things went pretty well. And off Dove 1 on the left, which was our better spacecraft, we got this picture. And so if you compare that to the PhoneSat 1, there's quite a difference. Much narrower field of view, much higher resolution. So this is a Douglas fir plantation in Oregon, Oregon State. And you can see there's trees, individual trees, groups of trees, clear areas, clearings, there's roads and trails. And so this image sort of really stood for what we wanted to do, which was to create high-resolution maps of the Earth. So we got this picture about 4 o'clock in the morning, and I emailed it to my business partner, Will. He was asleep at the time. He woke up at about 6:30, checked his email as he always does in bed, and he told me he started crying. He stayed in bed for 2 hours crying, looking at this picture because he was so moved by what we'd done. And this single picture really stands for everything my company is about, which is being able to look at our Earth, the trees, the forest, our landscape, and our impact on it, and maybe help us do that a little better. And in fact, if you look on Google Maps, there was some areas of this forest, particularly up here, that had been cleared since from the last picture to this one. So it was really sort of cool example of what we thought we could do with our products ultimately. So anyway, that was successful. Next step was build a lot of them. And so we have a little satellite factory downtown in San Francisco. The mayor came around a couple of months ago and he took a tour. And now apparently, whenever the mayor of San Francisco goes to other mayoral conferences, he brags to the other mayors, I have a space program. So we apparently the San Francisco Space Agency. So we make these downtown, right next to the Tenderloin, if anyone's been there. And have since then been launching them. So this is another flight of the Antares rocket, where we launched our first 28 sort of spacecraft in a constellation. And this is a little different than the other 2 rockets. In this case, the satellites went up as cargo in this capsule that was going to the International Space Station. This is a new opportunity for launching CubeSats. So it's actually a really cheap, really fast way to get a CubeSat into orbit. Is as cargo, the astronauts will actually take it and put it out of the hatch. The Russians actually threw one like football about 2 months ago, but ours are a little more orderly, and they come out of this automatic dispenser pod here. So this is a video, real video, from the station as 2 of our satellites come out. I like how he winks goodbye. Yeah?
Were those both your satellites?
Both of ours, yeah.
Is it helpful to have 2 cameras right next to each other?
They'll spread apart over time. And so after about a month, they end up randomized around the Earth's orbit. And so when we put out 30, they end up roughly about 10 degrees apart each over time. Yeah.
So the solar collectors on that, they're not oriented anyway. You just randomly catch sunlight.
No, our satellites have a full 3-axis control system, and they can orient and face the sun. So usually we have camera pointing down, solar panels rotated towards the sun, and then when we pass our ground station, we actually track the ground station and sort of pivot over it. Yeah.
Do you have any control over where they go?
So you can't, they don't have propulsion, so we can't change the orbital plane, but we can change the spacing, and we do that with differential drag. So we can rotate the solar panel's edge onto the wind. The atmosphere at 400 kilometers is still there. It's tenuous, but there's still pressure. So we can rotate edge on, sort of stall like a hang glider. And then, so for instance, when we launch 30 sats, we'll take half of them, put them edge on. Those will fall down and go into a shorter period, and then sort of race ahead. And then we'll put them back to low drag when we want to stabilize them for operations. But
What's the altitude of your orbits?
so the first 2, those are at like sort of more like 500, 600 kilometers. The space station is 400 kilometers, and so the trade-off is the lifetime is very short from station. And
That's from the surface, not the center.
yeah, 400 kilometers above the ground. Yeah.
I was going to ask what the lifetime is.
Yeah. So in the high orbits, it's about 4 years. In the station orbit, it's like 4 to 8 months. So the satellites actually don't last very long if you put them in a low orbit like this. So it's sort of like a trade-off between getting started and bang for the buck, really. Here's another video. I like this one. This was hand shot by one of the astronauts out of the window. And you can see 2 more cubes going off there. I think that's kind of neat. And because the other rocket's sort of automatic, there's no humans on board and everything sort of happens on a timer, you don't ever really get pictures. So these videos and pictures like this are kind of priceless. And we really couldn't pay any marketing firm in the world enough money to create something as amazing as this. So I think it's very grateful to NASA for doing this for us and making this opportunity available. And you guys, if you have a CubeSat, you should totally try and launch it this way. It's a great way to get to space. And another picture, just a close-up, taken also by one of the astronauts of the sats just above the Earth.
Those are 3 unit?
Yeah, so they're about this big. And so just what's this all for? So I showed you one of the pictures before, but we really want, with these satellites, to map the whole world. So in the last couple of months, we've started doing operations in sort of like large groups and trying to stitch together mosaics. So this was one of our first tests. So we tried to take an image of the Suez Canal, which we thought would be really interesting. And it kind of looks like this. So this is about 20 images stitched together. Is that playing? Let's try again. So you can see boats in the canal. You can see their wakes as they're moving. You can see sort of desert and farmland. See a split, more boats. Another boat. That one doesn't look like it just started moving. This one's moving quite fast. And then these ones sitting in the bitter sea are not moving at all. And so you can actually see ships that are waiting to sort of for their turn to go through the canal. So if you're an economist and you want to know global shipping volume, or maybe you're running a hedge fund and you want to see where stuff's coming to and from China, I think our data could be really helpful. Another example, who likes coffee? Yeah, I've got bad news for you. So this is the Minas Gerais reservoir in Brazil, where about 30% of the world's coffee is grown. And you can see the reservoir here. If everyone's dizzy, I'm going to play this one the other way. And if you're not dizzy, you will be after this. But you can see in the reservoir, like this sort of greenish stuff here is the water, and these are the high water marks from different years. So this reservoir is at a record low right now, which is really bad news for coffee farming and other kinds of industries. So it's kind of cool. You can see the whole reservoir, you can see bits of land. In some of our photos, we can compare, month to month changes that are happening in the levels of agriculture, who's farming, which crops are being harvested, which ones are struggling. I think this is just really pretty as well. It's one of the things that you sort of saw in the middle there. Hang on a minute. Let's skip that one. So also in Brazil, who remembers the World Cup beginning of last year? So there was a lot of news. There was some bad news, right, about building stadiums and workers' rights and homeless people and people in the barriers being moved out. So it's kind of interesting that you might be able to see that from space. So if you look in this blue circle here, it's this blue sort of shape, looks like Kentucky. This is Sao Paulo, and in that area, if you look at one of our photos, you can actually see the whole piece of city was removed and replaced with parkland. So now you see it, now you don't. So this is still ongoing news today, and indigenous rights and the rights of the unemployed and the homeless in Brazil is still a very big human rights issue. So it's interesting that you can see economic stuff, you can see humanitarian stuff, you can see stuff we care about like coffee, and you can see the plight of other people, all from space. So with that, I just wanted to finish, and happy to take any questions.
We have a good time for an extended question and answer session. Let's start with Steve. Yeah.
Could you talk about the imaging system? And I assume you don't use phones anymore? You have...
Yeah. So phones are kind of great to get started, but they're a little bit annoying because they only have one plug. And so if you want any kind of sort of connectivity, you need to move away from phones. And so we mostly build our own computers these days. So we have a lot of electrical engineers on the team. But we actually run like a regular workstation. So our satellite runs Ubuntu operating system. Can actually log into it. I can SSH into it from the ground. And the cool thing is, once you have a generalized computer, you get a lot of inputs like USB, Ethernet. We actually connect to our camera over the Ethernet. So the camera is an industrial grade CCD. It's like a really big, high quality CCD, but it connects to the computer via Ethernet. And so we're one of the first sort of people to ever actually just fly Ethernet as a regular data bus on a spacecraft. And it just works fine. It's like really no issue at all. It uses a lot of power, but it's still okay. The nice thing is then, what the spacecraft system looks like, kind of just looks like a webcam in a computer. And so you can actually think about satellites more like just glorified webcams in space with a bit of storage and a radio for getting the data. And so it's not very spacey. Also, the satellite is completely aerospace free. So there's not a single component in there that comes from the aerospace industry at all. It's all off the shelf. It's the same supply chains as the parts that make my laptop, basically. And so that means you just don't have to just like the phone. Most other stuff, this laptop is probably as good in space as my phone is. So that means you can build stuff cheaper. You don't have to. You can stay right on the cutting edge of Moore's law. Our hard drive on the spacecraft, we actually use the MacBook Air solid-state drive. So whenever Samsung or the vendors make a new upgraded version of that drive, we get it too. And we actually get it about a month before it actually ships. So our satellite had a 480 gigabyte solid-state drive about a month. We're in orbit using that about a month before it showed up in Mac stores for people to buy. And so sort of the advantage of just using pure commercial stuff is you can stay right on the front of sort of technology investments and build something really neat. And the system's kind of simple. It's a computer, not a spacecraft. So, yeah.
How much does each dove cost?
That's our one secret. I'll tell you almost everything else but that. So
Okay, the follow-up question. How do you have these connections with like Samsung to get
this is just vendors, right? I mean, we're trying to, now that we're getting a little bigger, we're starting to like get visited by some vendors who like want to make special arrangements with us, but we're actually kind of small. I mean, Dell will buy 50,000 or 500,000 or 5 million of a component. We buy 100, right? So we're actually not a big customer. So we mostly buy from resellers, so like McMaster-Carr and DigiKey, we use a lot. And some of the more expensive stuff like hardware, the solid-state drives come from other sort of suppliers who just buy them. I think maybe our batteries we get directly from Panasonic, but that's about it. Oh, yeah.
What is your market?
Our market? Yeah, so we're not a space company really, we're an imaging company. And so we sell maps. So we sell, just like those two examples, mosaic base maps. So we sell national base maps to countries. We sell specifically monitored data to NGOs and nonprofits who want to monitor deforestation. We work with agriculture companies around the world to build value-added products for their ag clients, precision agriculture, farming practices, things like that.
I want to follow up on working with vendors. Are there vendors who want to get their hardware space qualified? I mean, that process. You don't have the same hurdles that NASA imposes on itself at some level, right? To say this needs to be space qualified in this way. But one imagines vendors can see this as, the future looks brighter for this. And so I'm wondering if that's part of your discussion with vendors, or as far as they're concerned, you're a shipping address and a paying customer, or do you have talks with some of them where they said, yeah, we'd really like to see our solid state fly? And,
a little bit of both. So on our main computer, we're actually we have someone else who's developing computers for drone companies. So he wants it's a similar sort of capability computer. It's going to be mostly selling to drones, so drones is a bigger market than space. But he thinks the space part will help, and he wants space customers. And I also like his computer, so we've modified one of our satellites actually just last Friday to take his computer instead of ours. And it works more or less the same. Oops, there were some issues, but once we get those resolved, we're going to launch it and see if it works for him. And if we like it, we'll buy a small batch of them, maybe 100, and then he'll be able to tell his other customers all the space issues are resolved, works in space. So it's starting to be a thing people want to see. In front of you?
Yeah, do you have a marketing department? Like, for example, Sierra Club. They'd love to have images of what's happening in the rainforest. Do you have somebody going out and marketing your product?
Yeah, we have even better than that. We have a what we call impact team, and their job is to go and find non-commercial users who want our data. We really started the company mostly for the humanitarian and environmental reasons, not for the commercial ones. So the commercial ones pay bills, but our personal motivation is to actually help people and help the world.
Right.
So we have a pretty big team that works with places like Rockefeller Foundation, Gates Foundation. I don't know if we specifically talked to the Sierra Club, but they're the kind of people we would talk to. Once we get a little more sort of ready for prime time, we're going to actually release our data out more publicly, so universities, academic institutions, etc., can get it for free, and just go into the maps and play with them. We aren't quite fully operational yet, but that's coming soon. Down here?
So I have two questions. The first, am I right with the impression that you're trying to create a frequently updated map of the whole world, not just individual areas, but get enough satellites up that you can get a whole world map? Yep. So then my second question is, what frequency are you aiming for updates of that? Like,
that's a great question.
How often are you trying to roll over images?
So the question was, are we mapping the whole world instead of areas, and then what frequency? So most satellites that have flown before for Earth imaging are really expensive. So $3 billion, maybe Landsat 8 that launched 24 months ago last week was a $10 billion program. So if you're launching satellites that are that expensive, you can't launch a lot of them because of our undisclosed price point. We're not quite $3 billion per satellite. So if you're making them in the Tenderloin, they're probably not anywhere near that. So that means we can launch a lot of them. And And so big satellites, because there's few of them and but there's a lot of customers, they kind of have to like jump around all the time taking photos. It's kind of like a point and shoot camera. Like, hey, look, there's North Korea. President wants a photo. Bang, let's take that. Oh, here's something else. Let's look over here. And so there's a huge opportunity cost when you're jumping around all the time, taking one photo here, one photo there. When you have, what we intend to do is actually get to about 100 satellites. With 100, you don't have to pick and choose anymore. And so if you put them all in a ring around the Earth, and then as the Earth rotates once a day, you can actually scan the Earth like a line scanner. So the reference design for our company is whole Earth, 5-meter resolution, every day, every single day, with a repeater once a day. So those photos, we'll get those daily for every region once we've gotten over 100 satellites. Right now we have about 20 operational sats, and that gives us about monthly update of the whole world. So, up the back.
So I've got almost part 3 question to that. You mentioned a choice of lifetimes between a few months in low orbit and much longer in high orbit. So do you anticipate having to keep replacing these if you want your 100 Earth coverage, or is that going to be a permanent fixture and you expect them to last very long times?
It's largely limited by launch availability. So if we can find a rocket that will actually take 100, say, and adding in spares, more like 130, to a good orbit that'll last 4 or 5 years, we'll take that. If we can't find such a launch, then we'll build it out of bits and pieces out of different rockets. So we'll launch 10 here, with 10 here, 20 there, which we've been doing currently. And then it's a balance of lifetime and amortization rate and replenish cost. We're still cheap enough that equation works out favorable, but it is a shame to basically burn up satellites every 6 to 9 months.
And if you can't tell us your price cost, can you tell us the rough launch cost per kilogram or per satellite? How much does it cost to put it up there?
Yeah, launch is pretty well known. It's typically between $200,000 and $300,000 per 3U, and so it's maybe 70 to 100K per 1U. Nanoracks prices are close to that. They're the ones that do the space station launch. Direct rocket launches can be a little more expensive, maybe as much as 400K, I think, for a 3U, but sort of in that ballpark. So actually, if you think about that, it's an interesting point. The phone sat, so the satellite cost $3,000, remember? And the launch was about $70,000 for one of them. So for $75,000, you can put your own satellite in space. And that satellite was beeping. We had ham radio operators picking up the data. So it was kind of like Sputnik, except it had a camera. So it was Sputnik with a camera. So it was really better than Sputnik. And so for $75,000, my team of about 5 people did what the Soviet Union took 10 years to do and all of their resources. So each one of you, pretty much, if you just ask your parents to mortgage your house, has more capability than the Soviet Union had at the start of the space race. Which is kind of mind-blowing when you think about it. And so if you really, if my goal was to convince you to start, a company like mine, you can. And you can get started pretty cheaply. In the scheme of things, finding 75K for a space company is not a big deal. And so it's kind of neat to think that you've got that in your pocket. So, yeah.
So do you go to international conferences, so you get the international audience?
Do we?
Yeah.
Yeah. I was in Singapore and Malaysia and Japan in the last month, talking to people there. It was kind of fun. There was a big space conference in Canada I went to 3 months ago. And then our data is global, right? So our salespeople travel a lot. We want to sell into every country.
Good.
Yeah. Middle?
Do you operate your own ground station now?
Yes, we do. Yeah, we have about 14 ground stations around the world. Different countries: Australia, New Zealand, Germany, England, Canada, US. We have one in Hawaii, which is everyone's favorite. Whenever it breaks, there's a line of people waiting to get plane tickets. I always find that when someone's gone to the Hawaii ground station, mysteriously 4 other people have taken leave at the company, and somehow in the calendars it said out of office in Hawaii. So it's a good gig doing the ground station team. Over there.
Could you talk a little more about the radio system up and down?
Yeah. So there was no radio available for a CubeSat that could do what we wanted, so we had to build our own. We looked at all of the vendors that sell CubeSat stuff, and we considered. Actually, I can probably wake this up. Go back to that picture. We looked at all of the stuff that was out there, and all of it was too big, right? And our telescope is so big it takes up about 75% of the satellite volume. So
Could you say that again?
the telescope
Telescope is
the telescope for the camera is so big it takes up about 75% of the internal volume of the CubeSat. So there isn't room for any of the standard boxes of stuff, like a box, radio in a box and a control system in a box and reaction wheels in a box and a computer in a box. We didn't have anywhere to put those boxes. So we had to build everything ourselves and make it fit. And if you think about MacBook Airs or your phone, not everything in the phone's new, right? We've had GPS for a long time, we've had computers, we've had memory, we've had storage, had cameras. The miracle is that they fit. And so the iPhone is kind of like a miracle of packaging. And so our challenge was to make everything fit in a box. Well, actually, not even a box, like in the cavities and nooks and crannies around the telescope. So there was no radio, of course, that we could buy. And if you do the numbers, so the Earth, if you just look at the land area of the Earth, there's 145 million square kilometers. And our pixels are 25 million square kilometers. So that works out, if you do all of the numbers, about 2 terabytes of data a day. Circa 2012-ish, the total volume of data collected by all CubeSats was 2 gigabytes. So, 2 gigabytes, and we needed to collect for all of our satellites 2 terabytes a day. So we had a small numbers game problem. So there was no radio out there that was even going to do anything close to that. NASA has some really nice X-band radios that are like the size of a toaster oven. So those aren't going to fit, but they have the performance we wanted. So we decided to build our own. And so in this picture, we have 2 radios. This is our UHF one, which is common on a lot of CubeSats have this. We use this for our primary sort of commanding and for telemetry. But down here is a little helical antenna. So this is our X-band antenna. And so we built our own X-band radio that actually achieves 40 megabits a second from space. So that's faster than your home internet in most cases. So I was at a conference, actually it was the CubeSat conference in San Luis Obispo 2 years ago, and a gentleman was there saying that he thought that it was impossible for X-band to fit in a CubeSat and that it would never happen. But I already had one in space and had already used it and had 40 megabits a second. Anyway, this is a damn fast radio, and it's necessary for us to do what we want. And so we have some really cool improvements coming that I think I can get it up to about 200 megabits a second. Uses a lot of power, so I might have to make my solar panels bigger, but it does work. The other cool thing is the UHF radio, which is this antenna. When we first launched the first 28 satellites, they were very hard to find. And because the orbit is low, 400 kilometers, there's a lot of drag, and so the satellites the orbits decay slowly over time, and so the uncertainty of its position increases as time goes on because there's random drag forces and so on. So it's kind of hard to solve the equations and work out where it is. And NASA, every Christmas they do the Santa tracking thing, right? So NORAD tracks Santa. They track satellites, but they're not very accurate. And so we would get the satellite data from NORAD telling us where our satellites were, but it'd be wrong. And that affected the quality of our radio link. And so if the satellite was, say, 5 kilometers ahead or behind where our ground station thought it was, we wouldn't exactly be pointing at the antenna, and the signal would be really bad, and we wouldn't get much data. So we ended up building our own radio ranging stations. And so we used the UHF radio and the time of flight of light to actually send a ping and a pong back to our ground stations. And then if you do that across an orbit, you end up getting about 2,000 data points of time of flight. You can actually pin the position down to about 10 meters. And so this radio has built-in, essentially radar ranging. So that's kind of really cool. And we're actually going to open source this because we think the CubeSat community could use it, because finding a satellite is one of the hardest things once you launch it. And so the UHF radio, probably in about a year from now, we're going to package up and open source so that you can just take it and use it in your own designs. I think it's being able to find your satellite quickly, particularly for student projects, is really important. So this will really help do that. Cool. Come on. Yeah.
Would you mind also elaborating on how this is all deployed? So I assume the X-band antenna isn't poking the lens in the eye.
Oh yeah, cool.
The UHF flips out.
I don't have a good picture of that, but
The cells are wrapped around the thing and then they fan
yeah.
into a flap.
Yeah, so there's a hinge here, and this whole thing flaps down, sort of folds down, sorry. And where the antennas are, it also acts as a lens cap for the telescope when it's folded down. So this all folds over. Kind of looks a little bit like a toilet lid. And then this is actually really important. So this, when it's folded over, actually runs along this solar panel to about here. And there's a little hole here where we can attach a bone wire. So like basically it's the nylon wire, and there's a little resistor there that we can run about 40 amps through and cut the nylon. And so we can tie that down here at this point.
So they both deploy from the same.
Yeah, and then these three solar panels fold up. There's hinges here, they'll fold up, and then there's another little nylon wire here, so those will fold on the side. So when they're folded up, they kind of look like that, sort of body mounted, and then they sort of flip out once we're in space. But the problem is, in space there's sort of like a rule of thumb, which is any kind of mechanism is bad, right? Because you can't fix it, you can't go up there and fix it once it's in space. So if you mess up, you're kind of stuck. And so, just to be on the safe side, sometimes we don't include this piece of nylon, and we'll just let this automatically pop out. And so then what happens is this antenna, because it's rigid and it's folded over, kind of acts like a metering rod. So as you're sort of coming out of the pod, it has to travel half of the length of the CubeSat before this will just flip up on the spring. Yeah. And so this is sort of like our sort of lazy way of guaranteeing that the antenna always opens. Now, when I showed this video,
And that works with the space station launch, but not necessarily the rocket launch.
well, we do it on the rocket launch. We don't use the timer. We just do the physical, mechanism. So watch this again.
So the first one was open.
Yeah. So so see that popped out in the video there, and so why we did them differently was to spread the risk. We didn't want the, sorry, try again. Is that playing? Yeah. We didn't want the back one to hit the front one, so we put the burn mechanism on that to hold it. But the front one, we were like, well, we don't want them both to get stuck, so let's hedge our bets and have one of them open automatically and one of them be delayed. And that's why one spins, because when the antenna comes out while it's still half there, you add some angular momentum to the spacecraft, and then it clears, and it ends up getting a kick. And so the front one spins, the back one doesn't. And it's pretty predictable, so you can see it in this one too. And that one's got a very gentle spin. Yeah?
Were you able to ensure, like, mathematically that it wouldn't just run into the other satellite and completely throw it off the orbit?
Nope.
Just took the risk there.
Yeah. We did some modeling. The main thing is with the space station is you don't want those satellites one orbit later to come around and smack the space station in the back of the head. And so this is actually pointed downwards. And so you end up going into a lower orbit and up. And our CubeSat has a different drag profile than the space station. So after about one orbit, because they sort of co-rotate, right? That's a very slow relative velocity, so they actually co-rotate and slowly drift apart. So it's not one orbit, it's not like the station stationary and that thing goes around like that. They actually go like that. And so it takes maybe about 2 weeks before our satellite has lapped the Earth and come back around. By that time, drag has eroded our orbit to we're about maybe 20 kilometers below the station. So that's pretty predictable. And if that doesn't work, the station has boosters so it can lift itself up and miss us anyway. So by tracking the satellite, you get about 2 weeks notice if something's going to go wrong. The other thing that's really important that you sort of touched on is space debris. So we've all seen Gravity, right? I actually haven't because it terrified me because it's my job. But I refuse to watch it. But anyway, debris is a really big problem in space, and our strategy for dealing with debris is that because the orbit is low, if there was a collision, the debris wouldn't stay up for very long. So just like that movie WALL-E, where they're going out through Earth and there's just like soda cans and everything in orbit, right? Tons of junk. That's a really big problem. And at about 1,000 kilometers, a piece of debris will last, up to 1,000 years. But at 400 kilometers, it'll only last, 3 or 6 months. And so by launching low, our debris clears up. So I like to say low Earth orbit washes away all sins. So if we actually have a collision, it'll clear up after a short bit of time, and we won't have prohibited humanity from going to space. It'll just be a short-term inconvenience rather than a long-term risk.
Well, let's thank Dr. Boshuizen.